Namaskara. Welcome to Real-Time Digital Signal Processing first live session. So first, we will see the questions which has arrived. So the first query is suggest the textbook for any source for CCS V5 software and related programs. So what answer what I've given is Real-Time Digital Signal Processing Fundamentals Implementations and Applications, 3rd edition, Sen M. Co., Bob H. Lee, and then Wenshun Tian, Wheelie publication. And the next textbook, what I have referred is Digital Signal Processing, a Practical Approach by Ifiker, 2nd edition, Prentice Hall. The third one is Digital Signal Processing and Applications with OMAP L138 Experimental, 1st edition from Ronald Tree. So this has been because I've used for all lab applications LCDK 6748 board. It is almost equivalent to this OMAP L138. So we have used LCDK 6748 from Texas Instrument. And for checking our all algorithms, we have used the MATLAB and Code Composer Studio V5, what I've used in simulator up to 5th version. You can use them in simulator. And if you want to have hands-on experience for the TI 6748, what I've used is the Code Composer Studio version 9. So one of the thing what you have to keep it in mind here is these boards, even 6713 works with compiler version 7.4.4. So if you are having the higher version, please see that you load the compiler version 7.4.4 and then you use make it as default and then use them. So the second query what I've received is, Madam, why we are going for DFT from DTFT? So as we know, DTFT is discrete in time, whereas continuous in 4 years there. So that is the reason why, which is not possible for us to implement in the hardware. So we have to have both discrete values in time as well as in the frequency domain. So hence, both magnitude and frequency has to be completely in digital domain. So we move on to discrete Fourier transform. So we'll discuss a little on the assignments. If you have any queries, please be posting it. So I'll take them one by one. So till then, we'll discuss about the assignments. We had a few clarifications there also. So the first one is in a DSP processor, if A has M bits and B has N bits, the question was maximum number of bits required to represent their product is, because we take M plus 1, M plus N bits. If both are of the same units, that is both are N units or M units, then we have discussed in the class that our product to be represented, we need to be in bits, if you remember. In the case of 4x4 Braun multiply, number of adders are actually, the answer is 9 full adders and 3 half adders. If you take the last adder as a half adder, then it becomes 8 full adders and 4 half adders are also correct. That answer is also correct. Okay. So if next question was scaling is preferred due to trade-off between overflow prevention and then accuracy. So one has to consider, as we discussed in the theory, that we will be foregoing little on accuracy, and we are trying to avoid the overflow which is occurring, which will we have seen that it from completely positive value to it may go down to the negative value. So which we are trying to avoid it, and then with little bit on trade-off, we are going to take it in accuracy. So the next one is special addressing modes of DSP processors. As we discussed, most of it is addressing modes are we have is other processors also and microcontrollers. In this case, the special one is the circular addressing mode to cater to restrict our input data, what we are getting it in real time, to the length of whatever filter what we have defined, or if it is a filtering operation, or if it is Fourier transform, what we are doing it. So we'll be restricting to the length of n bits there, even the input, so that our memory is not going to overflow. Okay. There is a query that 4x4 cron, please explain with the diagram. So we'll go to the this thing, PPT later. Can we discuss this later? I'll be opening the Braun multiplier PPT. So, and then we'll explain the thing with respect to the diagram. Then you may be becoming clear with respect to that. So the next problem was what is the meaning of the parallelism? So which are correct statements, what it has been asked actually. That this thing in this case is algorithms can perform more than one operation by the increasing the speed. So this was discussed in the class, and then we can do the same operation at the same frequency by lowering our energy consumption. So that is what the two answers are correct in this. And we said if a sum of equal products to be computed using a pipeline MAC, and then MAC execution take 15 nanosecond. So what is the total time in microsecond required to compute the operation? So in this case, already we had given that answer has to be in microseconds. Few have them have written it as microseconds also. I think there was a glitch in the software that it would have taken it as wrong or whatever. So we wanted you to give the decimal correct value, that's all. But few of you have given the thing which is correct. So we said that we need, because after multiplication and addition, so which is going in parallel, so the last, if you remember the thing, this is k is equal to 0 to n minus 1, x of n minus k into h of k is our computation, y of n is equal to. So the first accumulator, we have made it as 0. Okay. So accumulator will be 0. And then after multiplication, it will be adding parallelly. So once this is done, the last operation, what we need is one more addition will be left out. So we have to account for after whatever our 0 to 511. So the 512th operation, we need to add the last one to get the correct result. So that's why we take it as it is 513 into 50 into 10 power minus 9 seconds, which is equivalent to 25.65 microseconds. So we said if MAC operation is conducted using 2 MACs, the time taken for each product is, in this case, it is 40 units. We have ignored all the other computations. So we require 40 units. If you go back to the notes, you will be seeing that 2 MAC needs 40 units. And the next question was, suppose we consider 8 registers to store the incoming values. What is the value? Now 13 is stored in which register? So we have to do it is bit reversal, what we'll be doing it. So if you write the 13 value in the bit reversal, so it is 8 plus 4, 12 and 13. So when I do the, because for the bit reversal, it is 8 by 2, which is 1, 0, 0. What you have to add it. In which register it is going to be stored. Okay, so what we have it is, as you can see, questions. Okay, So because 13 can be represented with, I'll call it as 4 bits, okay, what we need it. 4-bit means it is going to be 16 values, what we can represent the thing. So if we consider 100 is 16 by 2 is 8 is the value what we are going to have it. So then when I add with it, 1 plus 1 is 0, 1, and then 1, 1. So the answer is going to be, in this case, it is the 7th register what it will be holding the result value in the thing. Correct answer has to be 7.
It was corrected as 5.
Maybe
we have taken different way here, but it is
okay.
corrected as 5.
Okay, we have corrected it as 101. If it is 13 cannot be represented in the 8-bit, okay, it has to be in the 16-bit. So the register should have been 16 registers basically. So there was a error in the question, so it has been ignored, okay. So if we consider this as a thing, the answer will be 7 in the case, okay. As you can see that 1011 is the correct value for 30, and then when we represent in the 16-bit thing, so I have to add 100 to it, so it will be becoming 01. Yeah. So in the bit reversed addressing, if the input index is 101, what will be the output index? What it is asked. In this case, as you can see that it is 101. So if you add, because we are considering only 3 bits, in this case, we'll be adding 100 to it. 1 plus 1 will be 0. And then result is going to be 011 in this case.
The correct answer, we have shown it in the PPT. In the PPT, we have shown this is 101. At presentation, this is 10.
There should have been. In the Q15 format, so what is the addition of 0.375 and minus 0.250 is being asked actually. So in this case, the value is, as you can see that if you do the addition, so you will be having 0.375 is nothing but in the 15 format. So the rest of them become 0. So I'll be having 0.25 plus 0.125 will be your 0.375. So which is equivalent to 0.011, and rest of them 0 is what you can represent for the Q15 format. And minus 0.250. So if you take the thing, this is 0.01 for my what I'll call it as in the positive thing. So and then for the negative, I have to take the 2's complement for this, and then we'll be adding it. So if I take the, I have to put rest of the zeros, as you can see. Cross it, sorry, so that all the 4 bits what I can represent continuously for our Q15 format. So this is the value. So if I take the 2's complement of it, so it is going to be 1, 1, 0, and 1, and these are all 1's. So then I have to, that is 1's complement. When I add this 0, 0, 0, 4 zeros, 1, 2, 3, 4 zeros, 1 here, 1 plus 1 is 0, 1, 1, and then 1. Okay, so this is the value. So you will be adding with 1.1 here. So you'll be adding with the thing 1 plus 1 is 0, 1 plus 1 is 0, and 1 plus 1 is 0, and 1. This is going to be discarded. This is the value. So which is going to be 0.001, and then all zeros. So which is a positive number. What we'll be getting it, as you can see that 0.375 minus 0.25 has to be 0.125. So you have got the result correctly. So if it is the negative number, then our negative bit will be continuing. So next question is binary number 1001 in 2's complement is represented as, you will be seeing that this is 2 power 0, and then you will be continuing 2 power 1, 2 power 2, 2 power 3, 4, 5, 6, and then okay. So you will be seeing that this is a negative value, what we'll be representing, which is as minus 127. Okay. So why would one use fractional representation instead of integer representation of numbers? So we have the answer, correct answer, we have shown with the example that no overflow is going to occur in multiplication. So we cannot avoid the overflow in addition, but definitely we'll be avoiding in multiplication overflow. Coming to the next one, why would one use fractional representation instead of integer representation of numbers? So here also we'll see that there is not going to be any overflow in the multiplication part of it. So that is why we use the fractional representation. So that is next one is decimal equivalent of the floating point number with BIOS 7 for 1011. What you have to say that what is the exact value of it. So if you can answer, correct answer for this was minus 0.84375. So you will be taking, first is the negative number, sign bit is 1, you can see it is a negative number. And then the BIOS is taken as 2 power 3, you will be seeing it minus 1. So it will be 4 bits what you will be considering for the your exponent, and rest of them are going to be for the fractional number representation. So if you solve the problem what was given in the example what we considered in the class, so based on it, so the result has to be for minus 0.84375. That is what the result. And coming to next problem, so this is the binary number was given, and if you are shifting it right by 5 bits basically, so you'll be seeing that these all 5 bits will be going discarded, and last one will be there, and you will be adding. There will be 6. You can see the thing. What is it? Because 5 bits and 2 zeros are there, there will be 7 zeros, and last one will be 1 is the correct answer. Next one is how would one increase the range of numbers that can be represented in integer fixed point format by, usually we double the size of it to increase the range. So coming to the second assignment, so we have FIR filters can be derived from analog filters. Definitely not only IR filters, we'll be deriving it from analog filters. So it has to be designed using a windowing technique or any other algorithms to design our FIR filters in the digital domain itself. And then we said a general FIR filter has a linear phase response. It is false, because if you consider symmetric FIR filter, that is property is considered symmetric property, then FIR filter has a linear phase. Otherwise, normal FIR filter will not have a linear phase. So that is the explanation for it. And a group delay is given by the positive slope of the line. So the thing is false in for the thing. So it is going to be the negative slope, what we'll be considering it. And coming to the magnitude and group delay of high pass filter, So the answer in this case is, yeah. So as you can see, the example has been considered here. So you will be seeing that it is h of n to e power minus j omega n. And then you're considering this is a high pass filter, e power minus j omega, e power minus j omega 1. And then this is 1 minus e power minus j omega. And you will be seeing that what we'll be getting is 2j e power minus j omega by 2 into sine of omega by 2 is the thing. And its group delay, you will be seeing that negative slope, what we have to consider the thing, d phi omega by d omega is going to be equal to half. So your this thing, we have taken the absolute value of it. So sine omega by 2 and half will be the correct answer. Coming to the next one. So this is discussed in the class also. So if I draw a cut set here in the feed forward path, as you can see continuous, then the delay is going to be 2 units. That is, if you consider traveling to any of the nodes, so you'll be seeing A3 to A5, and this one is going to take 2 clock cycles. And from this to, if you are traveling to A6, from the delay unit to this node and this node, it will take 2 units. So maximum in this case is going to be 2 units and minimum can be 1 unit. But it is asked maximum delay, so 2 units is the correct answer. Continuing with the thing. So we said that linear phase is usually it is straight line in the passband of the system. So, and then we can have the answer that is non-straight line in the where is it, stop band of the system. We are not bothered about what kind of straight line we are going to have it in the stop band, but truly we want a straight line in the pass band. So these 2 answers are correct. So we have discarded the option. So you will be seeing that 1 and 4 are correct answers. Now coming to this problem. So you have 8 units, multiplication takes 8 units, and the adder take 2 units, and the desired clock period, what we want is 6 units. And which are the correct values of M1 and M2 in the following figure, what it is asked. So because we say we want every clock cycle our output, so we need a 6 unit from any of the unit what it should be happening. So we see that our multiplier, so this will be making it as 6. And then this multiplier is going to be 2 units. So that along with the adder, so it will be 2 plus 2 will be 4, and maximum is going to be 6 units. So that's why we'll have multiplier M1 with 6 units and M2 with 2 units. Okay, one more way of representing it is I can take this as 4 units. And then I can take the other multiplier as 4 units. Then 4 plus 2 will be my maximum delay. So these are the 2 ways of representing our multipliers with bifurcation, that is fine grain parallelism, what we can do with the thing. So both are the valid options. Coming to the next one, this is the problem what it was given. So it is 2 into 5 beta minus 0.6 whole squared, which is equal to this. It is the normal operations, appropriate value of beta for operational purposes. So what will be resulted with 0.0239 and 0.6033. So when I multiply 0.0231 with, because this is voltage with respect to 6 volts, and then you will be seeing that minimum what we need is threshold voltage is 0.6 volts. It should be more than that value. So this option will not be holding good. So hence the value 0.6033 is the correct answer for that. And we said critical path in pipeline processor can be shortened. How we can do that? That is inserting gates in between. It is not correct. And insert the latches in between combination logic circuits is not correct. So we'll be inserting either latches or register. Both are valid. So in between combinational logic circuits is the correct answer. The transition band of filter increases as order of filter decreases, which is true in this case. As you will be seeing that this is my transition band. As the order is of the filter, this thing order increases. Filter order increases. So this is going to be shortened. So more we'll be having the cutoff with the thing. This is my transition. Next, we'll discuss the assignment 3 actually. So the with respect to 1/4, the answer was given, but in the thing figure, it came out as 1/8 itself. So whatever we discussed in the class, so the correct answer is, I think it is minus 0.183 and then 0.683 is the correct answer, because there was this thing, a mistaken thing. So this question has been withdrawn. So if you take this equal to my 1/4, then you will be getting the second answer is the correct answer. So we have asked which are the correct answers if you have been given a to the power of n u of n. So if I do the z transformation, so which is given by 1/1 minus az minus 1 for magnitude of z in the z domain greater than magnitude of a. So what we say is the filter is going to be stable if magnitude of a is less than 1, because we know that our circle is unit 1. So all the poles fall within the unit circle, then we say the system is stable. If poles are outside the unit circle, then we know that the system becomes unstable. To the next assignment, it is n is equal to 4 bits have been given, and we have given the full scale voltage of ADC, what it can be given by. We know that the correct answer is it varies from minus 0.5 delta to 15.5 delta. If you apply the equation, whatever is given in the thing, so it is going to be this value is the correct answer. So to achieve our maximum SQNR 90 dB, how many bits one must select for ADC? So we have the equation. When you substitute in that, so we'll be getting correct results as 14 point something. So B plus 1 will be 15 point something. So we have discarded the whatever the decimal points what we have got it. So 15 bits is the correct answer in this. So the next one, you have been asked to check that what is this figure represents. So as you know, can you guess the thing? This is a symmetric filter, as you can see. So you will be adding x of n and then x of n minus 6. This is, you will be seeing that it is an even symmetric filter basically. So you are adding x of n minus adding x of n plus x of n minus 6 and multiplying with your h of 0. And then the next one, you will be seeing that h of 1 is multiplied with your x of n minus 1 plus x of n minus 5. And then h of 2 is getting multiplied with x of n minus 2 into x of n minus 4. And then, sorry, it is a odd symmetric. Basically, you have a h of 3 in this case. So you will be seeing that h of 3 into x of n minus 3 will be the last one. So you will be seeing that this is n minus 1, n minus 2, n minus 3 here. And this is n minus 4. Output of this. Okay. So same x of n minus 5, x of n minus 6. So when you do the thing, the first answer is the correct answer. So number of filter coefficients, number of delay elements, number of adders, number of storage elements, and number of multipliers for the given figure are, what is it? So you can count the thing, how many adders I have it. Okay. So the last addition, if you take the thing 3 plus 1, 4 adders, what we needed. I'm going in the this thing. What is it? Number of adders, what I have given the thing, and number of delay elements, you will be seeing it as 6 here. Okay. And then filter coefficients. So you see that there are 4 filter coefficients. That is the first one. Next one is our number of storage elements, what you needed. So you need x of n. I need not have to store the thing which is coming in. So from x of n minus 1 to x of n minus 6, what I am supposed to store. Even yn, I don't need to store them. So I have to store 6 of them, basically. That is what storage. And number of multipliers, what you will be seeing is, if you count on the thing, so you'll be seeing 1, 2, 3, and then 4. So 4 multipliers. And storage, I have shown you it is 4. So the first one is the correct answer. Coming to our next problem. So you have been given h of z as 1 by 1 minus 0.8 z minus 1. Completely it is a all pole system, as you can see. 0.15 z minus 2. So what is the h dash in the 4-bit using direct form, what we has been asked. So when I represent this values to the nearest value, what I have to represent. So 0.8 can be represented as 0.875, and 0.15, what I can represent it as 0.125. I have taken little more than the thing here, and then little less than whatever. Next one will be 0.25, what I have to represent, which is much more. So the nearest what we have taken, trying to match at least with the first number. Here also we are trying to match with the thing. So this is the correct answer. And coming with the thing, so if I take in the second order thing, actually, using the system, how I can represent this h double dash. So I can split this into 0.3 and then 0.5. And then I can represent in a parallel fashion in this case. Sorry, cascaded form, what I can, if I take the thing with respect to 0.875, what we can represent is minus 0.25 into z minus 1 plus 0.5. So as you will be seeing, 0.5 plus 0.25, what you will be adding it. So 0.75 is the correct result. Okay, fine. Coming to the next one, the continuing with the thing. So what are the pole positions for A and B was asked actually. So if you take you will be finding the root of the equation. So you will be seeing that if it is not quantized, the pole position will be 0.64 and 0.234, and the quantized pole positions will be 0.25 and then 0.5, what will be the result of it. And implementation complexity of IR filter is almost lower by 8 times than that of FIR filter. So which is false. It is, we know that whatever implementation number of order of the filter is less compared to FIR filter, but we cannot say it is 8 times. That's why the result is false. And coming to assignment 4, what we have is, it is, we'll say that it has zeros and then poles. So what will be the fixed point 2's complement in 8-bit representation, what you have to put it. So if you take 1 is left out, then you will be allocating 1 sign bit, and then rest of the 7 bits can be for your fractional representation. So if you consider that B1, B2, this is the correct answer, what you can represent in the that is complete one, I won't be able to represent it. That's why the maximum value what I can represent is 0.111 is for the P2, as well as B0 if you are taking this also. And then B1 is going to be 0.0339. The nearest value what I can represent is with this number. So you will be seeing that this will be 2 power minus 1, 2 power minus 2, 2 power minus 3, and 2 power minus 4, and 2 power minus 5 is the correct answer to represent my minus 0.174, minus 0.0339. Okay. Scale factor for IR filter to be chosen such that the signal to noise ratio is going to be, what is it? We want to have the signal to noise ratio maximum. That's why it should be largest what we have to select the thing. So the same example has been given. This is for the zeros what you have represented and how I can represent the poles. So you will be seeing that if I take 1 bit per sign bit, same with respect to this and this, I'll be selecting the same thing. One of the thing is A1 is going to be, because it is a negative number, I have to take the 2's complement and represent, so which becomes this value. And A2 will be 0.96662. So you will be representing this with bits. So you will be taking this also 2 power minus 1, 2 power minus 2, etc. You can do the thing. And then when you add it up, you should be getting that result. And then the next argument was which scaling argument is true in IR filters. So we have discussed in the class saying that L2 has the least this thing. What is it? Scaling factor. So this will be less than L1, and then L1 will be greater than L infinity. So we had seen that L2 less than L infinity less than L1. So only L1 is greater than L infinity. So B answer is correct in this case. Coming to next one. So in figure, we have to say how many quantization points are there for a bounded input. All of us know the quantization is going to happen at the addition. So we have 2 addition in the second order section. So our quantization points are going to be 2. With whatever the maximum value, what we'll be representing it is going to be scaled, as you can see. And then it may be trying to overflow or underflow. In this case, both are negative. And then all of them are positive. These may be trying to overflow. So the quantization has to happen at 2 places. So it is 2. And we know that W400 is equal to WX800. So what is the value of X has been asked. So you will be seeing that it is a 4 into 8 normal and 2 zeros what you can cancel it. So it becomes 32 is the answer. X value is represented W32 in 800. So which is same as W400, twiddle factor. And DFT coefficients of a 5-point real sequence are given. So you have been given X of 0, X of 1, X of 3, and then now you have to compute your what is it? Input, that is X of 0. So you will be doing 1 by n sigma actually. In this case, it is a 5-point real sequences what you have been given. So when you try to put back in your equation or use your FFT filter, so you will be getting as 2 is your answer. When you apply your equation, X of capital N into, this is X of N is equal to capital X of N into e power minus j 2 pi nk by capital N. So we are trying to find out X of 0. So it is going to be 0 to n minus 1. So if you add them up, all of them are e power 0. So you will be adding capital X of 0 to 3, what you are adding it. So you will be adding 4 plus 1 plus 2, what I have it. So plus 1, so which is equivalent to 8 by 4, which is equal to 2. 2 is the correct answer. So you have to represent your X of 4 will be the conjugate of this. So, and take that value and represent it. So you will be getting this result as 2. So the next one is, we said that it is sample, we have capital N is equal to 512 points, and sapling is Fs is given as 8 kilohertz. What is this K value going to represent? So can you guess what is this? So which has to be 500 hertz. So if you apply your this thing, K is equal to N by Fs, that is 512 by your 8K. What is it? Did I apply the correct this thing? So it should be Fs by N, what you will be taking it. Sorry. Because I need in hertz. So 8,000 divided by 512, what you do the thing. So yeah, we can you can see the equation, and then we can calculate the K value from that. Okay. This is equal to 2 into yeah, we'll consider that later. I'll give the equation for that. So the next one is the frequency resolution of DFT for Q8 is given as it is 15.625 hertz is the correct answer. That is and how to do the circular convolution of sequences X of 1, 2, 3, 4, and then 1, 0, 1. So you can pad H of 1 with 1, 0, 1, and then 0, and then do the circular convolution. So moving one of the thing, the result is 4, 6, 4, 6 is the thing. So you can follow the example given in the notes basically. So that was a question. So we'll post the Braun multiplier. Okay, so you are seeing the Braun multiplier. So if I take, you have to show. Okay, so now you will be seeing the Braun multiplier. So the first one, what we'll be considering it as an half adder because 0 is the input. I don't need the carry input is not there. So there are 3 half adders here. So, and you can see that the last one, that is what I said. If you consider this as 1 half adder, then we'll be having it, that is one of the input is 0. Then it becomes 4 half adders and then 6 full adder, 8 full adders what we needed. So you will be saying this is 3 plus 3, 6 plus 2 will be 8 full adders. So I have considered this as also full adder. That's why the result was 3 half adders and then I had taken it as 9 full adders. So that is what the conceptual, if I consider everything as a full adder, I don't want to design the half adder because it's going to increase my, circuits within the thing, OR gates and then exclusive OR gates, what I'll be designing with the thing to get the result added then with the carry. So I'll be increasing my circuitry. If I'm allowed to do that, then I'll be considering all of them as 12 full adders. So if I want to reduce the thing, then I can go with 4 half adders and then 8 full adders. Is it clear? Zero is the input. Okay. So if it doesn't consider carry in for this, then it becomes a half adder because I'm only taking 2 inputs. Okay, it is not 3 inputs. So if we consider this, that's what I said. If we consider 0 is also an input, then it becomes the 12 full adders what we needed. Okay, to reduce the hardware. So I can have 8 full adders plus 4 half adders.
Ma'am, but we have to consider all has a full adders, no, ma'am.
Yeah, that is one thing. So to reduce your complexity, you can reduce the thing. So because there was little ambiguity, this has been withdrawn. Okay. So this question has been withdrawn. So because it can, because I consider this as a full adder. So people had given 8 half adders, 8 full adders and 4 half adders. And even if you consider this as also full adder, because you want to replicate them, because you need not have to redesign half adder, then it is 12 full adders is the correct answer. If you are considering that also is a full adder.
Okay.
Yeah, any other doubt?
Ma'am, while scrutining, have you considered this answers, ma'am? Means based on that, have you given the marks?
Yeah. That this question was withdrawn. Yeah. So I think so in the 3-bit, as you can see, 101, the input is also 5 and output is also going to be 5 in this case. X of k. What is x of k you wanted to have?
Actually, you have mentioned it has a x of capital N. It should be x of capital K in the equation while explaining.
Okay.
Ma'am, one more question. Wait for question 9. Can you explain it once, ma'am? Here you have given some combinations, IAR filter cascading. But now you have explained with some Q8. Can you please recheck it?
One second. IAR
Question.
filter.
Question
Question
repeat the
number?
question.
Week 4, question number 9, ma'am.
Can you call out the question? Like, which is the question?
Which combination is suited for IAR filter cascading?
Cascading, it should be a cascaded form, okay?
Yeah, the diagram forms.
Yeah, next one. This is how many quantization points? Which assignment you are talking about?
Ma'am, I'm talking about a week 4 assignment, question number 9.
Week 4 question number 9.
Are you asking about this in the figure? How many quantization points are there in the bounded input? Are you asking about that?
No, ma'am. Question number 9. Which
9.
combination is suited for IAR filter cascading?
Yeah.
Here Q8 is given, no, ma'am. That question was not given actually, I guess. Another question was there before this circular convolution.
Just a minute.
Okay.
Assignment. Open. It's two is not given. Good. Yeah, can you send me that question? I'll answer through mail. Okay. You can post that question because we are not seeing that question here with us. It is assignment 4 only. Bhavna? You are muted.
Yes, ma'am. It is assignment 4. Yes, ma'am. It is assignment 4 only. And 9th question it is.
9th question.
I'm just.
Yeah. Can you please post the question in the chat message, or we can you can post it on the forum, then we will answer via mail.
Ma'am, I'm trying to send, ma'am. Just a minute. Means I'm going there. 1 minute, ma'am. One minute, ma'am. I'm sending.
Yeah.
Ma'am, chat box is not opening. I don't know what happened.
We are also trying to log in and see. Yeah. By the meanwhile, you can post it here. Okay.
No.
Okay.
You are talking about the circular convolution. That is, we have the unit circle within which zeros and then poles have been marked. Is that one what you are asking?
Yes, ma'am, this one.
This one.
Yeah.
Okay. Well, the first one is the correct answer. So you, sorry, 1 second.
Yes.
A is the correct answer in this. Sorry.
Can you tell it?
Okay. So the one that is what we usually consider is the farthest to the zero. Okay, that is, this is our 0, 0. So from here, farthest, what we'll be taking this as my pole. So, okay. So you will be seeing that this is the this is the farthest from my origin. Okay, this pole. So the one which is farthest is combined with the 0 which is nearest to 0. And next one will be taking the next farthest, and then next nearer to 0 what will combine, and then the last one is which is in this case it has to be last one, because it is the 6th order filter. Okay, sorry, I'll call it as 6 into 2, 12th order. Basically, each is a 2nd order section because you will be having 2 poles and then 2 zeros in each section. So I discussed in the class, if you remember that, how we are going to combine, cascade the sections, and then how you will be taking the combination of poles and zeros to reduce the overshoot that is going to happen, because here they will be cancelling it out. So these two have to be combined. This is what it has been found in the literature basically. And next will be, this is combined with the next little nearer to 0. And then in this case, this is the closest to our origin, which is going to be combined with this farthest. So that is what the literature gives. But or the we know that IR filter exists more than 125 years. So how the combination has to be done is also worked out. So you can try it out by combining other things. There will be little overshoot from each section. So then you may have to quantize them. So minimum quantization with all the sections is going to be, if you combine the poles and zeros, what it shows. Otherwise, you will be running your software for various combinations. This with the other one. So you will be doing so many multiple times. And then to find out which is the which gives you more stable, as well as no overshoots and other thing is going to happen. So they have found out if you combine in this way, that is what the thing will be resulting in. Okay, this is how we take the combinations of the poles and zeros. Does it clarify?
Yes, ma'am. Can I know from which reference have you studied this topic, ma'am?
This topic is I have taken it from a TI website. They had given some study materials on the IR filter. Okay. So from there, what it has been taken. So if you want, I'll share that.
Please share if it is possible.
Okay,
thank you.
Fine. Okay.
Thank you.
Because I'll be taking from different sources. So
yes,
difficult to keep track of the thing. Hopefully this has been taken from there. Okay. Any more questions?
No, ma'am. Thank you. It was
Thank you so much for taking this course. All the best.
Thank you.